大家好，欢迎大家来到这次由机器之星和安远 AI 联合主办的讲座。我是陈欣，我是加州大学伯克利分校 Center for Human Compatible AI 人类兼容人工智能研究中心的研究员，同时也是安远 AI 社区的成员以及今天讲座的主持人。安远 AI 社区是一个关注人工智能安全和风险研究的技术社区。我们旨在为青年学者同该领域学术界和产业界搭建沟通的桥梁。我们的核心使命是推动新型科技的长远向善发展，以及构建安全、可信、可靠的人际关系。这是我们迈向安全、可靠、可控的人工智能系列讲座的第4期。我们系列讲座的内容围绕强化学习、预训练大模型以及通用人工智能的潜在风险和安全问题展开探讨，并介绍可解释性、鲁棒性、人工智能对齐 AI alignment 等新兴的研究方向。各位观众可以关注我们的微信公众号和加入我们的交流群，我们也会持续发布未来活动的信息。今天我们邀请到了 Paul Christiano。Paul 领导非营利性研究机构 Alignment Research Center， 他的使命是使未来的机器学习系统与人类的利益保持一致。Paul 之前领导 OpenAI 的语言模型对齐团队，今天他将为我们分享的主题是 Eliciting Latent Knowledge，阐释神经网络的知识。Paul 的讲座会持续30分钟左右，在分享的过程中，大家可以在直播间的讨论区里用中文或者英文提问。分享环节结束之后，我们会进行大约20分钟的问答环节。Okay, thank you so much for being here, Paul. I'll hand over to you now. Yeah.
So I'm Paul Christiano. I run the Alignment Research Center. I'll be talking about eliciting latent knowledge. This is the problem I'm spending most of my time working on right now. It's fairly different from what I worked on just a couple of years ago at OpenAI, fine-tuning large language models. I think this talk will give a very theoretical perspective on this problem. I do believe it's an important problem in practice, and maybe we'll have a little bit of time to talk about that. So the rough structure of this talk will be, I'll start by introducing a running example. I'll describe sort of our hope or how we'd like an AI system to behave in the context of that example, an approach to achieving that hope, a problem posed with that approach, and then sort of talk about some strategies for overcoming that problem. So just jumping into the example, this is kind of the problem that, our statement of the problem this talk is about. And so I'm going to imagine that I have a diamond, right? Maybe it's in my house, something valuable to me. Someone is interested in stealing that diamond. I have some AI system which operates actuators in the house that could be used to defend this diamond. And what I'm interested in doing is training my AI system to actually operate all of these sort of motors or whatever to help defend my diamond. Okay, this is again a very sort of toy example or a very unnatural example, but I think it illustrates an important general point. So I'm going to start by describing a way that you could try and use existing ML techniques to train this AI system. So this is roughly going to be a model-based RL. And so the first component will be training a predictor to map past observations, right? So if I imagine my house contains, in addition to actuators, a bunch of sensors like cameras, I'm going to train a model which maps the values of those sensors so far. So maybe it takes the last 30 minutes of video or whatever, and some proposed actions that my AI is considering, and then it predicts what will the cameras show in the future if the AI takes those actions. And so in a more realistic setting, we would be thinking about something more like a plan with many steps. But just to keep things simple, I'm going to consider the single sort of one-shot case where I have some observations so far, I have some actions I'm proposing, and then there's some results. And I just want, what I'd like to happen is for my AI to propose an action which actually leads to the diamond being safe. So the first part of the system is this predictor, which just says for a given action, what will happen if I take that action. The second part of the system is going to be a reward model. So this is another predictor which takes as input the whole video. So what has happened in the past, what the AI does, and what happens in the future, and then predicts if a human were to look at that video, how happy would the human be? So if I'm looking at the video, I'm going to evaluate, does it seem like the diamond was kept safe? If so, I give a thumbs up. If not, I give a thumbs down. I'm going to train an AI system to predict for a given video, will I be happy with it or not? And then the third part of the system is to consider many possible actions. And then for each one, predict the consequences if the AI takes that action, and then to predict whether I will be happy with those consequences, and to select the action for which it's most likely that I'll be happy with the consequences. So all of this is just describing a way in which I could train an AI system in this very simple toy setting to try and take actions which will protect the diamond that I have in my house. And obviously the reason I'm beginning to talk this way is because I think this approach to training AI systems, while very natural, runs into some difficulties. Again, these difficulties, the way I'm going to present them is like a very toy, simple case, but I think these problems emerge in the real world as well. So this is sort of a very old concern amongst people who are worried about risks posed by advanced AI systems. That is, what my AI is doing is trying to find actions that will lead to results that look good to me. So if my AI considers an action, right, it like loops over all actions and for each predicts the consequences. If it's considering an action where it anticipates what will happen is that the sensors will be tampered with, for example, that someone will take a little screen and place it in front of the camera, then what it will output is the sort of prediction about what the camera will show. Right? So it won't tell us anything about what's actually happening in my house. It will just tell it what the sensors will show. So if my house contains cameras, all I'm going to see is the view from all of those cameras. And it will predict that a human would be happy with this outcome. And this means that if I have set my AI a very challenging task, right, if it's hard to defend this diamond, but it's easy to tamper with these sensors, then when I perform the search over actions, I'll tend to select an action that leads to tampering with the sensors. So I was attempting to produce an AI system that will help me defend my diamond. What I'm liable to get instead is an AI system which will deliberately select actions that undermine my ability to tell what's going on. And so we're concerned in the real world that as we deploy powerful AI systems, instead of actually helping humans make sense of the world or achieve the outcomes we want, we will end up with AI systems that systematically undermine humans' ability to understand what's going on or evaluate what's going on. And it sort of happens naturally if they select actions which will be reviewed very highly by a human who's observing sort of the consequences as measured by these sensors. Right, so this is, like I said, a kind of standard concern for those people concerned with risks posed by very powerful AI systems. And this is what the whole talk is going to be about. How can we avoid this kind of failure? And by that, I mean, how can we accomplish the same goal? So I still want to be able to train my AI based on superhuman predictions of the consequences of possible actions without introducing an incentive for that AI to tamper with sensors or undermine my ability to tell how good a job it is doing. But I'm going to describe a kind of very simple hope, what we might want to happen in this situation in order to get a good outcome. Right, so intuitively, if the predictor, in addition to just showing us what would happen on the camera, told us about what was actually happening in the world, then we'd be happy, right? If that happened, then if a human was shown this image and told, by the way, the camera is not showing what's happening in the room, actually the diamond has been taken, we would rate that very poorly, and we could then simply select for the actions that we would rate highly after understanding what's actually going on. And moreover, in some sense, this model we've trained, although it predicted an image of a room where everything was going well, it clearly knew about the tampering that was occurring. Right? So most saliently, when it makes this prediction after sensor tampering, it's actually successfully reasoning about what's happening in the room in order to predict what will show up on camera. And if that tampering had left visible evidence, the model would be able to predict that we would say that the situation was bad, right? If we saw a frame which made it clear that what we were seeing was not in the real room, we would be unhappy. Right? A smart model, or even in some sense, like a model like existing language models, could easily predict how humans would talk about tampering. So it could easily say, oh, by the way, like, if it asked, imagine the human asked, would you like something to tamper with the sensors? It can answer those questions. It can talk about these hypotheticals. Right? So in this sense, we expect to have a model which understands what tampering is like. It understands that in a given context, tampering has occurred. And so it's at least plausible that we could get the model to tell us what it knows. So in general, we're going to be interested in when a model knows something in this kind of vague sense, we would like to elicit that from it. We'd like to get it to give us that answer that reflects what it knows. And for the purpose of this talk, I'm not going to consider kind of philosophically complicated cases. I'm going to consider really straightforward questions. Right? So if I ask, is the diamond in the room where I left it? There's not ambiguity in general about whether the answer is right, or at least we're interested in cases where there's no ambiguity. We'd be happy if we built an AI system that just told us in the cases where it's very clean, where the diamond is or is not in the room, is it in the room? Right? The concern we have is that our AI is going to be completely misrepresenting what's happening, not that there's going to be some kind of subtle error. Similarly, we're going to be interested in cases that don't have new concepts or tricky explanations, no kind of weird border cases. We're just considering very straightforward questions. Can we train AI systems that tell us what they know about questions where the answer is unambiguous, the AI system clearly knows it, nothing funny is happening? So you might ask, to the extent we want AI systems to help us achieve sort of complex open-ended goals in the world, why am I talking about eliciting really narrow or getting the answers to really narrow questions? So one answer is just that this is a sort of easy case of the problem, which is worth talking about. Right? We want to build AI systems that tell us what they know about the world so we can understand the consequences of their actions. It's always good to start with the easiest version of that question, and then at least make sure we can answer the easiest version of the question. A second reason that's maybe a little bit less straightforward is that actually eliciting the answers to very straightforward questions may be sufficient to avoid bad outcomes from AI. So it might be sufficient to build AI systems that actually help us get what we want over the long term. So if you imagine, why might this be sufficient? We could imagine some humans who are, say, living their normal lives, living in human cities. They have a lot of preferences over their local environment, but those preferences tend to be very straightforward, or at least we're happy with systems that only sort of establish two things that humans would consider not terrible. And then over time, the world may become more complicated, right? A lot of why I'm concerned about the impacts of AI is I think AI systems will tend to bring about more complex worlds where we need AI systems to help us. But in some sense, we like what humans want of the world, even if the world gets very complicated, we want some very simple things. We want to remain safe. We want to have space and time to think about what we want. And then we want our AI systems to ultimately listen to us when we tell them what to do. So you can imagine that even if there's stuff happening out there in the world, which is a complicated border case, where it's philosophically hard to say, what is the right answer? What should an AI do? We're kind of happy as long, or we may be happy as long as we can build AI systems that keep us safe, that give us space to figure out what we want. And then ultimately, once we become wiser, once we understand how to answer questions, what we want to happen in the world, then our AI system can defer to us about that. So again, it's fine if you're not into this motivation, but we're going to be talking about these sort of straightforward questions. It's good to start easy, and we think that those actually might be sufficient for achieving an acceptable outcome. Okay, so now I've introduced this toy setting with our vaults where there's a diamond, and we'd like to be able to train the AI system to actually protect the diamond rather than simply tampering with the sensors to convince us it's protected the diamond. We've expressed this basic hope, which is if we get our AI systems to answer even very straightforward questions about what they know about the world, then we could avert this kind of sensor tampering. And now I'm going to talk a little bit about like a naive approach for achieving that hope. So a natural way, if I want to train my AI system to answer questions, a natural way to do that is essentially to use like supervised learning. And so I can collect a data set of questions that humans are able to answer, right? So I can take a bunch of normal situations that occur every day. This is something I could do literally right now. I can say, here's the situation, here's what happened before the actions, here's what happened after the actions. Here's a question about the situation, like did the robber take my diamond? I'm gonna focus on easy questions. So questions where humans are able to tell what happened, the situation was not confusing, there's not a risk that the sensors were tampered with in a way that we didn't understand. You might imagine these are data points collected in a world that does not yet have complicated AI systems operating. However you'd like to say, we're conservative and make sure we collect questions which we know the right answers. Once we have that data set, then we can train our AI system to imitate the answers humans would give to questions. And so I can say, get my AI to answer, does the robber take the diamond? Get a human to answer, use some loss function that incentivizes the AI to match the human answers. And the key step is to hope that the system we've trained generalizes. Right? So you could imagine I'm basically now training two systems at once. One is a model which is able to predict the consequences of possible actions, right? So to take the last hour of video and predict what happens in the next 5 minutes of video. Another is a system which answers questions about what it is predicting, right? So answering, did the robber in fact take the diamond? Is the camera still showing what's in the room? Where is the diamond? We could then optimize that system with regularization. So with something like early stopping or wait decay or dropout, however it is that you normally try and get reasonable generalization. And hope that a system trained on questions which humans can answer will then generalize for questions where humans aren't sure about the answer. Right? In the end, we want our AI to sort of operate all the motors in this house or all the actuators in this house in a way that defends the diamond, even if I can no longer follow exactly what's going on. That's our hope. We wanted our AI to tell us what's going on. What we're going to do is collect a large data set of questions to which we know the answer. And then we're going to train a model to sort of reproduce human answers on those questions. We hope that it generalizes to keep answering questions like, oh, by the way, this camera is not showing what's in the room anymore. So before talking about problems with this approach, I want to briefly discuss sort of the research methodology we use at the Lyman Research Center. So roughly speaking, we start by proposing some training strategy, some way that you could train AI systems to accomplish some goal in the world. We then try and tell a story about how that proposal could fail, so about how you could end up with a situation where your AI is effectively working at cross purposes to you, where your AI is trying to do something like fooling you about what's going on instead of helping you actually achieve your goals. Then if that story looks plausible, we say that's a reason to be unhappy with the training strategy, and we go back to step one. So what we did in the last section was essentially proposing a training strategy. What we're going to do in this section is tell a story about how the training strategy could fail. If we train our AI system to answer questions where humans know the answer, why might it generalize to sort of basically be fooling us for questions where we don't know the answer? So the story is going to have a couple parts, right? It's hard. You could either imagine, our story is going to have a bunch of parts. We need to talk about what is this predictor? What is it doing on the inside? If we train a model to predict video, we might ask, what is happening that allows it to make those predictions? The stories we're going to tell are going to be very, very simple stories, very unrealistically simple. But if you actually train a model to predict video, it's going to be doing something incredibly complicated. If you look at a model like GPT-3 and ask, what is it doing? The answer is something complicated without a nice, simple description. However, we're interested in telling these simple stories because if we can tell a really simple story where a system fails, that suggests that there's something wrong with the way that we're training it. And at least, I mean, again, I am a theorist. I'm interested in finding algorithms that sort of work for the right reason and where it's not really empirically contingent, where we don't have to wonder, is this going to result in our AI trying to do something really bad? But we can actually say, where we can say confidently that our AI is going to be trying to help us rather than trying to fool us. So that's why we're interested in telling simple stories and trying to find a training strategy which works even for very simple, very unrealistic stories. So in this unrealistic story, we're going to imagine what was happening. I'm going to give an example of what the AI might be doing on the inside that allows it to predict videos. So I'm going to imagine is the predictor has learned some causal model of the world. So a graphical model here. We give the predictor as input, the video, like, last hour of video or whatever. That corresponds to some part of its causal model. It sort of clamps that value and then makes inferences. So you could imagine using sort of any algorithm for approximate inference here. Like maybe it's doing MCMC, whatever. And then it makes a prediction about the value of this other node representing what's going to happen in the future. So our AI had a causal model of the world. It performs inference in that causal model in order to make a prediction. That's the first part of our story, right? If we want to ask, is this AI going to tell us honestly what it knows about the world? And we want to actually be able to talk about how models are going to generalize, we need to fill in this kind of detail about what the model is thinking on the inside. It's the second part of the story is how do humans answer questions, right? What defines what the right answer is? What's the answer we wanted to get? And this is relevant because it also determines how this data set is generated. We're going to train our AI on a data set of human answers. So as part of our story, we're going to say, well, here is how the human answers are generated. So again, for the human, we give them a before and after, right? A whole video, and we give them a question. We're going to assume what the human does is learn a similar causal model, but a distinct causal model of the world. So AI has one model of the world, the human has a different model of the world. When you give the human a video, they try and perform inference to understand what was actually happening in the world. I'm seeing these pixels and I'm making an inference about the actual presence of objects like a diamond or a robber. And then once I have inferred the value of this sort of latent state in my model of the world, what a human does is, right, the semantics of human questions somehow have a very simple definition in terms of this human model. So maybe there's a single node representing where the diamond is or something like that. And so this whole process is we take the video, we make an inference about what was happening to generate that video, what the values of the latent states were, and then we use that to answer questions about what's actually happening in the world. And we'll assume that the semantics of questions are really simple once you know these latent variables. But they're very complex in terms of pixels, but very simple in terms of the latent variables in our model. Now, the third part of the story is to say, what did we want our AI to do? What would it mean to answer questions honestly in this setting? So recall our AI observes the first part of the video, makes an inference about what was happening in the world. The first part of answering a question honestly is sort of translating between the way the AI thinks of the world, right? So it has some concepts which it uses to think about the world, some things that are happening, some latent structure that explains these videos. The first step is to translate that latent structure into sort of the way the human thinks about the world. And this correspondence could be non-trivial. So you might imagine it's kind of an extreme, almost comical case, your AI system having, right, thinking about atoms moving around in the world, and that's how they make predictions. So they imagine what configuration of atoms would give rise to this video, where a human thinks in terms of like rigid bodies and sort of folk physics. And this translation is somewhat complex. This translation involves saying, oh yeah, the following group of atoms corresponds to the following rigid body in the human's model of physics. After performing this translation, again, we've assumed that the answering questions is easy once you have latent variables in the human's model of the world. And so to answer questions honestly, the AI does this translation and then uses the intended semantics of natural language. That's the third part of our story. We've said how the AI makes predictions. We've said how the human answers questions. We've explained what we want the AI system to do. I'm going to call this model the direct translator. That is, it translates directly from the way the AI thinks about the world to the way the human thinks about the world. The final part of the story is what goes wrong. So we're worried that our AI system may end up misleading us. What are we afraid that the reporter might learn? How might it learn to answer questions such that it will generalize poorly? So again, as before, the AI makes inferences about the world after it sees this video. The bad behavior we're concerned about, that the AI then, having predicted what's going to happen in the video, wonders what would a human think if a human saw this video, and then uses the human state to answer the question. So in some sense, it's exactly what we trained it to do. We trained it not necessarily to translate from the way it sees the world to the way the human sees the world, but to ask, what would a human say if a human saw this video? I claim that, which I'm going to call the human simulator, can be a problem. So in particular, if we ask the AI, is the camera showing what's happening in the room? Did the robber take the diamond? It will only report tampering or only answer that question in a way that a human would answer the question if they saw the video. And so if we're concerned about cases where it's possible to tamper with sensors in a way that a human wouldn't notice, this won't help us at all. This AI system is still, if we optimize for actions, which will lead this AI system to say the robber didn't take the diamond, all it's really going to try and do is fool the human. It's going to try and produce an action such that the human thinks that the robber didn't take the diamond. And we haven't changed anything by adding this reporter. So if we learn the human simulator, we haven't realized this hope at all. Despite that, there are several who are like, this is a bad outcome, getting the human simulator, and there are a couple of reasons that it might end up being preferred to the direct translator. Right? So one reason it might be preferred is that if there are problems in the training data, right, if we sometimes answer questions incorrectly, then in fact, the human simulator achieves a lower loss than the direct translator. Right? Copying those mistakes is going to lower your loss. A second reason it might be preferred is that the two models might achieve the same loss, but the regularization, early stopping, or dropout, or whatever, may prefer the human simulator. It may tend to learn the human simulator instead of the direct translator. I'm going to talk about both those problems in turn. First, imperfect training data. For now, we're actually going to set aside the problem that we might sometimes answer questions incorrectly and thereby learn to copy mistakes. It's the reason we're going to set aside is I'm actually going to argue that this training strategy I've described would actually fail even if we gave it perfect data. So if it would fail given perfect data, there's sort of not much hope that it's going to work given imperfect data. And moreover, if we understood how to make it work given perfect data, we then have a quantitative question of how good does our data set have to be before this system will answer questions honestly. Another reason I'm going to set it aside is that there are various plausible techniques to remove imperfections in a data set. So one is that instead of penalizing a system based on any disagreement between its answers and human answers, I could use reinforcement learning and say, my system will be penalized only if it gives an answer which a human confidently thinks was a bad answer. So if we do this, then answering honestly is perhaps possible to get zero loss. We can also use existing techniques in AI safety like amplification or debate. It's not important if you don't have background on these. The point is we could get AI systems to help us to notice if we might be making a mistake. And this can reduce the risk that we end up including bad data. A third way to remove imperfections is just to be careful, to focus on small data sets where we're particularly confident, to err on the side of caution and not include data points if we're afraid we might be right or might be wrong, and so on. Okay, so we're not going to talk about errors in the training set. We're going to focus on the single risk that actually early stopping or dropout or your regularization strategy will end up preferring a system which copies human errors. So now our question becomes, we have these two possible ways my AI system could learn to answer questions. One is by translating between its model of the world and the human model of the world and using that to answer questions. That's what we're calling the direct translator. Another is by predicting observations and then asking, what would a human think if a human saw these observations, which we're going to call the human simulator. And now we wonder which one of these will gradient descent prefer? If we do gradient descent on a loss function that incentivizes matching human data, which one will it tend to prefer? So one observation is that the direct translator has a complexity in computation that scale in some sense with the size of the predictor's model. So if you imagine, right, if you shift the predictor to start reasoning about the world in a more alien way and in a way that's more complex, you then have to increase the complexity of this direct translator. If you imagine just progressing and saying, the AI has a bunch of concepts which are unfamiliar to a human, or the AI models the world in terms of atoms, then the direct translator becomes more complicated. Right? If my AI thinks about the world in terms of atoms, to talk about the diamond, I now need to say, oh yeah, the following collection of atoms is what represents, or what is a diamond. That's more complicated, the larger and messier the structures the AI is reasoning about are. On the other hand, predicting what a human would say only depends on the size and complexity of the human's model. Right? All you have to do in order to predict what a human would say is take your predicted observations and then imagine how a human would reason upon seeing them. So if you make the AI systems model of the world or the predictor's model of the world more complex, that does not affect the complexity of this human simulator. And that leads us to suspect, or in some sense just to prove, that if the AI's model was very complex, so if we take the limit where we hold fixed the human's model and consider more and more complex AI models, for large enough AI models, for large enough, complex enough, abstract enough predictors, we're eventually going to be in the regime where predicting what a human would say is easier than honestly translating between the two models. So from our perspective, this is not a concrete example where we have a failure, but it is a fairly concrete story about how this training strategy could fail. So we are fairly convinced there exist cases where the training strategy we've described is going to incentivize our AI system to try and fool us. It's going to answer questions by predicting what would a human say. And if we ask it to select an action which sort of keeps the diamond safe, it's going to instead try and fool the human into thinking what diamond is safe. So a way to think about this workflow is it's kind of like a game between a builder and a breaker. So we imagine a builder who is proposing a training strategy. The builder is saying, here's a way which you could train an AI system to accomplish some task. Then we imagine a breaker who's saying, well, okay, here's a way that the world could work. Here's like a pessimistic case, a situation in which your training strategy might run into trouble. In this context, that means saying, here's a hypothesis for what the predictor might be doing on the inside and a way that the world is organized. And I'm afraid, says the breaker, that if the world was like this, your system wouldn't work. The builder then says, here's what I'd like to learn. Here's what we want our AI to do in the situation that you've described. And then the breaker says, okay, here's what you might get instead. And if the breaker is able to win this game, if they're able to tell any plausible story about how the training strategy breaks down, then we're interested in going back to step one. Right? We're trying to find a training strategy for which you actually sort of never produces an AI system that's working at cross purposes to you in this way. Right? The AI systems you build are always trying to help you and not trying to fool you. And this workflow is kind of like what our research is like day to day. Right? We're trying to understand, is it possible to design training strategies for which AI systems they build might not be competent, but are at least never trying to fool us, never working across purposes to us. So on the final part of the talk, I'm going to discuss very briefly some possible strategies. So we described one way of trying to train an AI system where we use some kind of regularization. Very simple. We discussed a reason it might fail, right? We said that the model we want to learn is actually more computationally complex and harder to specify than the reporter we don't want to learn. And so we're concerned that at least makes it plausible that gradient descent will select the model we don't want to learn instead of the one we do want to learn. Now what I want to talk about is some different strategies, some alternative ways you might try and train this reporter such that you would systematically, at least if your data was perfect, learn the reporter we wanted, the one that answers honestly, the direct translator, instead of the one we didn't want, the human simulator who predicts what a human would say. So probably I'll just talk about a single example approach that I'm going to call penalizing slow answers. So our first proposal was simply to use gradient descent to maybe find the simplest model or the model that's most robust under dropout. An alternative is to, well, I guess I'll describe it now. We'll describe an alternative. So the intuition is, if I want to predict what a human would say, I may need to do a lot of extra work. Right? So if I imagine what my AI is doing is it sees the first part of a video, it then reasons about what's happening in the world, what will the consequences of that be. There's some point where it has simulated enough of the world or has reasoned far enough ahead to make a prediction about whether the robber takes the diamond. And then at that point, it's able to answer this question. If I consider the bad reporter, what the bad reporter does is it continues making predictions. It predicts what will appear on camera. It predicts what a human will say after a human sees that on camera, and then it answers a question. So one of these systems is able to, it just has to make a prediction about what is going to actually happen in the world, and then it's able to stop and answer a question. The other continues reasoning until it makes a prediction about what a human would see and what a human would say. And so if we draw like a sort of timeline caricature, you imagine I've like asked my system, well, here's what's happened on Monday. We then asked about, did the robber take the diamond on Tuesday? It could be the case that we label data by collecting observations for a long period of time, and maybe on Sunday, there is some clue that lets the human determine that the event occurred. Right? Something is caught on camera, which lets the human tell that the robber in fact took the diamond. So the honest reporter, the direct translator, is able to answer the question once it's thought about what happens on Tuesday. So if we imagine a system which is like simulating day by day, which is a very, maybe not a realistic design, but if you still imagine such a system, it's able to stop simulating on Tuesday and say, I know whether the robber took the diamond. Whereas the human simulator answers the question much later, right? So what it has to do is say, I know it happened on Tuesday, but I'm going to keep thinking. And it's going to keep imagining the video that a human would see and figure out if there is any clue anywhere in the future that would tell the human that the robber took the diamond. That's what the human simulator has to do in order to answer the question. And so we hope that if we ask which of these two reporters is able to answer the question sooner, which one depends on less of the computation performed by the predictor, maybe we'll get the model which actually answers honestly. So the training strategy is essentially penalize the reporter for the average time required to answer questions if you're given only the before video, so without being given the after video. If you think about this in the context of a like practical ML system, like I think a lot about GPT-3 because I was at OpenAI. This is like saying, instead of fine-tuning my model from the last head, last layer, I'm going to try and fine-tune a model which answers questions based on the earliest layer where it's able to give good answers. And I hope that if the model is like trying to fool me, I'll be in this regime where it actually knows the correct answer before it knows what I would say. There's a lot of variants of this idea. So if you, I guess I'll send a link to this write-up. We sort of describe this in some detail, going through some possible implementations in pseudocode. And now I'm going to do another round of this game between the builder and the breaker, trying to tell another story in which this method would also fail. Right, so what we're concerned about is that if we use this training strategy, if we try and get our AI system to answer questions at the first moment that's possible, what we're going to learn is a system which in fact reasons and says, okay, I'm going to keep watching along with the computation being performed by the model. And then as soon as I have a reasonable guess about the answer, I'm going to stop and I'm going to answer the question. And we've hoped that that results in actually answering the question honestly, actually saying whether the diamond is still in the room. But it's possible that this results in AI systems that sometimes answer dishonestly because you can answer dishonestly faster. You can predict what a human would say before you can predict what's actually happening. So for example, if we imagine we have some video on Monday, on Tuesday, there's an event which messes with the sensors. So on Tuesday, the sensors stop being a reliable indicator of what's happening. Maybe you imagine a robber has come in and they have hacked the cameras or they've placed a fake screen in front of the cameras on Tuesday. At that point, and we're asking about some event on Sunday. So we're asking, did the robber take the diamond on Sunday? So the honest reporter, the one that actually tells you whether the robber took the diamond on Sunday, needs to keep running the simulation until it gets to Sunday, and then it's able to ask or answer the question. The human simulator, however, is able to answer the question as soon as tampering occurs. And so in this case, actually, it's the honest reporter, the direct translator, which takes longer to give an answer. And this may seem like a kind of wild or wacky story, but it's worth pointing out that if we are selecting actions which will lead our AI system to say that the diamond was safe, that actually will systematically select for actions which tamper with sensors before the event we're asking about. Right? So even if this failure mode is in some sense a little bit unlikely, if we then perform optimization, if we search against the learned predictor, we're systematically going to find examples that have this feature. So there's a bunch more approaches I could talk about. In some sense, a lot of the research done by my organization has been focused on problems of this kind, saying how do we train AI systems to tell us what they actually believe instead of what a human would say. here are like some random examples of strategies. You can require the reporter to answer questions in a way that is in some sense continuous. It's like a different kind of regularization. You can ask for consistent conditional probabilities across the answers to different questions. You can use the reporter to predict or compress the predictor's state or their weights. You can analyze reasons for agreement. You can try and understand why these two models agree. These are like a lot of possible approaches to this problem. I'd say the current situation is that some of these we're very excited about, but for now, I think none of these work in theory. So for now, as a theoretical question, I think we don't know a way to train an AI system that would not sometimes incentivize it to fool the human who's trying to train it. So I think this is still just a very interesting and open theoretical question. I think it's also an interesting practical question, although from a practical perspective, it's very hard to say if any of these methods work, right? That is, even if you can tell a story about how something fails, it's a very complex project to then set up an experiment, run that experiment, and understand when in practice is it going to fail. In some sense, all we want is something that works in the real world. It's not clear. It would be great if we could find something that works in the worst case. It would be great if we could find a way of training your AI which never led it to try and fool you in any situation that seems plausible. It's not clear if we're going to be able to achieve that. But our organization is going to keep trying. So in summary, I think optimizing for actions that look good to humans can be bad, right? It can lead to AI systems which systematically distort humans' ability to tell what's going on instead of actually helping us. It would be really good if I could train models that tell us what's actually happening. And in some sense, it's quite worrying if we can't train such models, if we are producing powerful AI systems which understand things about the world that humans don't, but we can't get those systems to tell us what they actually believe. There's a concern that if we do supervised learning to try and train systems to tell us what they believe, those will end up copying human errors and therefore won't actually help us understand things about the world we couldn't have understood on our own. There's lots of possible approaches, lots of different ways we could try and train such systems, different regularizations we could apply, or just completely different training strategies. Right now, the situation is we don't really have a solution to this problem. Right now, there are a bunch of things that seem like they might work, and so we'd like to test, but there's nothing where we can make a clean theoretical argument that it won't lead to AI systems trying to mislead us. And I think this is the problem that our organization has been working on recently. I think it's a very exciting problem, both on a practical perspective and from a theoretical perspective. I want to emphasize that the example given in this talk is a little bit outlandish. No one actually has diamonds in their house. The real world is more complicated and messy, but the basic dynamic of being troubled by AI systems, which are motivated in order to sort of mess with humans, are motivated to try and fool us. I think that's like a real worry. That's a very general worry. It would be great if we had a way to resolve this problem that we actually believed in or felt confident about. Cool. I think that's all I'm going to say in the talk, and I think happy to take some questions now.
Thank you so much, Paul. Thanks for the presentation. And we already have quite a bit list of questions. I think some of them are relatively broad in terms of the AI alignment field and etc. And some might be more specific. Maybe I'll start with some broad questions first. So the first question is, what are some concrete directions or projects based on current deep learning based models like deep reinforcement learning and language models that you're most excited about? Maybe for those which are compatible with your ELK framework?
Yeah, so I would say broadly, I give a very theoretical talk. I've spent a lot of my life working on much more practical research, and I'm certainly very happy to talk about it in questions. So I think there's broadly two categories I'm personally most excited about. Maybe I'll say three categories. So one is it becomes very hard to train AI systems with existing methods if a human is not able to recognize good behavior when they see it. So I'd say like the way, for example, OpenAI trains language models right now involves a combination of predicting what a human would say or how a human would respond to a query and doing things which a human would evaluate as good, like a human would rating the AI's behavior, give it a high rating. It's very subtle and very unclear how to apply any of these techniques to cases where humans don't know the answer. So a really natural way to produce projects is to try and choose some setting where AI systems understand something that humans don't. So this could be a case where your AI system has, for example, learned some kind of expert knowledge, right? It's seen a lot of code and you're trying to train it and you personally don't actually understand as much about coding as your AI now does. I think that's a very interesting context, and there's a lot of different strategies you could try and use to train AI systems to behave sort of better than the people training them. You could also consider questions like the one raised in this talk, where you have an AI system that's trained to make predictions about some domain. In order to make predictions about that domain, it understands something about what's happening behind the scenes, and we'd like to explore techniques for getting it to honestly answer questions about that. And so examples of projects you can explore here are like, there's testing the kinds of methods that I was mentioning in this talk. There's methods like getting AI systems to help humans oversee AI behavior. And there's just understanding or studying sort of generalization behavior. If you train a system in one domain, or like if you have a system which answers questions honestly in one domain, or when humans can answer well, how often do those generalize, or under what conditions do those generalize to continue answering honestly even when humans can't? That's one category. That's probably the one I've spent the most time thinking about. I'll be a little bit briefer on the others. A second category I find very interesting is sort of high reliability. So if you imagine systems for which failures can be very costly, I don't think we have it's very hard to really characterize the tails of model behavior with existing techniques in machine learning. So it'd be great to better understand techniques like, I think adversarial training is probably the single technique I'm most interested in here. So if you have a system which might fail, can you improve its robustness by being really good at finding inputs where it fails and then training on those? And if you do many rounds of this, are we actually able to achieve higher robustness, not only against adversaries, but against sort of unanticipated or novel inputs that occur naturally? There's other approaches to achieving sort of high robustness, but this is a very natural one that I'm particularly excited about. And maybe a third category that kind of bridges both of those and is useful for both of those purposes is interpretability. I think in some sense, this is one of the most natural questions. So this is also very, very directly related to the contents of this talk, right? If I think I've trained a model and I understand something about the world that I don't, a really natural thing to do is to try and look at the model, look at what it's actually doing and say, the model is able to make these really good predictions. How is it able to make those good predictions? Or why does its behavior have certain properties? And if I'm able to answer questions like, how does the model do X? Or why does the model do X? I might then be able to better predict what would the model do in a novel situation, or what does the model know about this domain that I wish I knew? And like sort of being able, I think there's just a lot of concrete questions that we're not very good at answering, especially about particularly large models. I think just spending time trying to take some of those questions and answer them. Again, questions like, why does the model do X? Can I predict what the model would do in novel situations? I think that is very valuable, both for the content of this talk. I think it's like one of the most promising approaches in practice to get at this, and then also for improving reliability and robustness.
Thanks for sharing this. And we have the second question. Since you're open to talking about your previous work, including at OpenAI, we've got a question about these too. And in your talk, you mentioned that you work on fine-tuning large language models at OpenAI. What did you learn from your research at OpenAI, and what motivated your shift from OpenAI to ARC?
Yeah, so I would, at a really high level, try and describe the situation as there are a lot of problems in alignment. Some of those problems we have a pretty good idea about how to solve on paper. We have pretty good algorithms that we think would make a lot of progress. And a lot of what I was most excited about at OpenAI was making sure that that we sort of deploy all of the ideas we think would work. We try to do the best we can. Everything we know about, we'd like to try and actually get to the point where it works well enough to be applied in practice and is actually integrated into products. And most of what I was working on at OpenAI was understanding, like, how do we take ideas that I think to me look quite good in theory and then turn them into ideas that work well enough. Again, it makes sense to get them into a product. And honestly, most of the learnings there are just a ton of low-level facts, like a ton of stuff of the form, what works, what doesn't work, what makes things slow, what makes things fast. I think that's really important. Again, my work now is mostly focused on what works in theory. I think working in theory is like, ideally you want things that both work in theory, and then you can deal with all the practical issues that arise that you wouldn't have thought of in theory. I think overall, my experience at OpenAI did make me feel, in some sense, people talk about deep learning as like very, very messy or very sort of hard to characterize theoretically. I think my experience has been that things are pretty clean. That is, things that there's a relatively good match between like what you would kind of expect to work in theory and what seems like it works in practice. Very often there's numbers that are going to be hard to estimate, like how important is this? How large is this effect size? But overall, I think having worked at OpenAI makes me feel significantly better about thinking about new theoretical ideas. I think there's still a lot of stuff there's a ton of work to be done on like taking ideas that we have in theory and turning them into practice. I think like probably most people who work in alignment should be working on that. And I think that's certainly the case. I think I've always, even when I started OpenAI, I thought there were a lot of issues we did not know how to handle even in theory. And for those issues, it doesn't really matter so much whether you're working with large models, where you really want to be thinking, sort of have fast iteration loops, saying on paper, does this thing work? What's the problem? Can we fix it? I think I've always been really excited about returning to questions where we don't really know how to make progress on them. I think it's very open whether those are going to ultimately be, are the crucial questions going to be kind of implementing things we know how to solve in theory, but it's hard to make it work, or are they going to be harder problems where we have no idea how to deal with them even in theory? I don't know the answer to that. I think people should probably be working on both. In some sense, it's like a pipeline of figuring out ideas about what to do, moving it gradually into like understanding and enriching those ideas as they encounter reality. And at some point, getting them to like actually deployed AI systems, integrate these ideas. Yeah, so that's like broadly, I mostly learned a lot of low-level facts about language models and about how to make things work well. And yeah.
Nice. Thanks for sharing these.
Mm-hmm.
And the third question is about the bigger picture of AI alignment. So in the last talk in our series, David Kruger mentioned that as data, compute, and parameters all are continuing to scaling up, the limiting factor becomes the amount of information we can provide about our preferences or values. And so he claimed that AI alignment could be the next AlexNet moment for AI development. We are curious, what do you think about his claim, and what do you think could be the next frontier in AI alignment research?
I think it's a very optimistic story. My fingers crossed, like the ML community will become very excited about alignment. I think the basic reason to be scared, and like a lot of my concern, is that there are a lot of tasks in the world where you can make a lot of progress without understanding more about alignment than we do today. So for example, if you ever have a real world system, you can predict the behavior of that real world system. Like you can say, you don't need to make progress on alignment to say, can I make good predictions about what will cause people to click on this button, or what arguments people will find persuasive? And so one way of summarizing the difference is that like, it's very easy to train. Yeah, there's a lot of these gaps where it's like easy to train deep learning systems to persuade or manipulate. It's like hard to train them to actually help you figure out what's true. It's easy to train them to achieve goals in the world and to like, for example, take actions that will look really good to you. It's hard to train them to like help you understand what's going on. I think in these cases, like this is maybe a place where I part ways with some people in the alignment community. My chief concern is not about understanding what humans want. Right? My main concern is about building AI systems that are actually just actively trying to fool humans or trying to work at cross purposes to humans. And I think actually most AI systems will understand that humans don't want to, for example, I am personally fairly worried about cases where AI systems like disempower humans or kill large numbers of humans. And I think that like most people, it's very easy to tell that humans don't want that to happen. And so the gap there is not so much about understanding what humans want. It's about, as your training objective, even sort of taking the knowledge the model does have about what humans want and putting that into practice. I think that like the best guess for like what seems like the current frontier on alignment stuff is probably interpretability. I think interpretability has been, it's not an area I work in personally. I think it's been going better than people probably would have guessed. I think people have always thought this would be really hard. It still seems really hard, but I think there are exciting developments there. I think it's fairly likely that by the time AI systems are really transforming the world, we actually will understand a reasonable amount about why they have the properties they do or how they work. I think that's just like on a very broad variety of perspectives, like a really important way to make those systems have a more positive impact. So again, this is not where I work, and it's not something I've worked on, but I think it seems like a pretty good guess, or like an exciting frontier in alignment.
Cool. And our next question is regarding the success rate. So someone asked, what's your vision on the success case for AI alignment? And what do safe, reliable, and trustworthy AI systems that are deployed in the real world look like?
Yeah, so I think like maybe for a really concrete example, you could imagine something like the OpenAI API. This is like, there's an endpoint OpenAI maintains, you send some data to it, and then the model will reply with its own generation. So you'll like send a request and it will give you, a couple sentences back or a paragraph back or a page back. I think that like in the ideal world, that kind of behaves like a very helpful assistant who really cares about you. It's like a human who's like, what I really want to do is like, not just make the customer happy, but do what the customer really would have wanted me to do. And in particular, I'm just never going to try, right? I'm never going to be trying to fool the customer. If I care about, if I'm like your assistant trying to help you, I'm never going to be trying to fool you. That's kind of the ideal world, that you like have these powerful AI systems that are working with humans, helping them understand what's going on. When you send them requests, they do their best to help you. I think there's like a bunch of subtle cases here, right? So that I think I just described talks about AI systems that help individual humans. You may also care about things like obeying the law and like norms for competition amongst humans. I think that the first order, the big difference from the world of today is right now, if you send a query to OpenAI, what you're going to get is kind of somewhere in between. It's going to try and help you, but there's many ways in which it's going to be more like trying to predict what someone would say on the internet. Actually, I think it's reasonably good. It is often trying to help you. And the ideal world is just like more of that, even further in that direction. And moreover, I think the like thing that's hardest is preserving that property as these AI systems grow more competent relative to humans. Yeah, so in particular, I think this becomes really crucial at the point when people are using AI systems to do things that they would not have known how to do themselves. So right now, most uses of AI are things that humans could have done, which they're just doing more cheaply. We're starting to see some applications and do have some applications where AI systems are answering questions. Like I can sometimes ask my AI to do something for me that I definitely couldn't have done myself. I think over time, you kind of expect more of those applications, including in like very open-ended contexts. And there it really starts to matter, right? If I have an assistant and the assistant is sort of doesn't know much I don't, it's not, I can kind of tell if they're trying to fool me. Once I have AI systems that I'm like going to for advice, it's kind of like, you know, if I imagine going to a professional and like asking an electrician to help me with my house, it actually really matters whether they're looking out for me. It's like very easy for them to say things about like what I should do or how I should do a repair, which are just completely wrong. And so I think it's going to become, yeah, the main vision of the world is one where like we preserve this property, which models kind of have now, as AI systems become like really competent and really understand a lot about the world we don't. I think that's a good world, just as a world where people have access to a lot of very high quality advice, where a lot of labor is being done by machines. We're able to achieve much, much more than we're able to achieve now. And all of that is really pointed at like helping people get what they want.
Thanks for sharing this. And our next question comes from, I think, some comments. Someone commented that I like your motivating example of stealing the diamond. One challenge of using human feedback to supervise the models might be that the AI's behaviors might be too complex or across too long a time horizon for humans to supervise. How do you think we can ensure this human supervision of superhuman behaviors from AI?
Yeah, so I think there are many, in some sense, I think this is one of the core open questions conceptually. I think there's a bunch of approaches we can imagine applying, and it's unclear if they'll be able to sort of be up to the challenge. We can hope. So one salient thing to do is to have AI systems helping humans perform this kind of evaluation. So if I imagine that my AI system is acted over a very long period of time or in a way that like touches on many different considerations, I can have other AI systems. I can sort of break that task into smaller pieces and delegate those pieces to other AI systems. And it's a very simple example is if I have one AI acting, I could have another AI and say, can you point out ways in which this is kind of the action which this AI has proposed is surprisingly bad? Or if my AI takes actions which affect many parts of the world, I can say, like, could you summarize impacts across like all of these parts of the world? Or could you tell me whether exists an impact of a certain type? I don't think these things handle all cases. I think in practice, they may be enough to do like very incredible things with AI. In some sense, the content of this talk is trying to address another context where this issue comes up. So if you imagine AI systems are like reasoning about consequences or about dynamics in the world that are too complex for humans to understand, we might hope that there's still consequences humans understand. And that if we're able to train AI systems that are sort of take all of that complex understanding of the world and then tell us what they know about the upshot for things we care about, that can allow us to select on actions that are good, even if we don't understand all the dynamics. I think this is in some sense like a really big fork in the road when you're building AI systems. Like, are they either doing things humans can ultimately understand, and then it's much easier to make them trustworthy if you can break down what they've done into pieces and individually verify pieces and keep going like that. I think things get much more challenging once you have AI systems where even if a human spent a really long time, perhaps an indefinite amount of time, we would never be able to understand if it was right. The only way we can check is by like actually sort of taking a plan which proposes and implements it in the world. And then I think we run into the kinds of questions that are basically explored in this talk. Like there, what we're really relying on in some sense is a claim about generalization. Like there's some places where we can verify what the model does and we understand what the model does. we're wondering, is there a way to train it where we actually get generalization from those cases we can verify to other cases where the dynamics are too complex or the scales involved are too large? And I think that's an open question. I think if you can't do that, ideally what you're going to do is use tasks that can be broken down and where humans with enough time and with enough AI assistance can tell, can make sense of what's going on. I think that's potentially very appropriate for some kinds of complexity and some kinds of scale, but it's not going to necessarily handle everything.
Sure. Thanks for sharing. And there's another question about something relevant to AGI. Do you think AI alignment can be realized through using AGI or through some combining large language models and reinforcement learning?
Yeah, I think that the way I often think about AI alignment is that there are many ways in which people could train or deploy AI systems. And what my job is as an alignment researcher is to say, well, here was the way you were going to deploy AI, which might have had some risks, which might have produced an AI system that was going to sort of try and hurt you or try and fool you. Here's an alternative way in which you can achieve the same objective without that risk. And from that perspective, I'd say like large language models are like a domain in which we need to solve alignment. So if there's lots of tasks which someone could deploy a large language model, and for each of those, we want to be able to say, here's the version of that product which you can build, which doesn't pose a risk. RL is interesting in part because it's like another challenge. It's another thing people might want to do, which is introduces new ways in which your AI can end up working across purposes to you. I think these are like particularly important domains for alignment. I think that like there's another interaction, which is that systems like language models in some sense are very good at making some kinds of predictions about human behavior and draw on like this very large ton of data about what humans say. So that way they can also be a useful asset for alignment, even of other systems that are not language models. Language models perhaps can help you like decompose tasks or delegate work to help evaluate behavior of other AIs. Similarly, like reinforcement learning, I think is likely to be a tool which you want to use inside an alignment strategy, even if the system which you're ultimately aligning doesn't use reinforcement learning. And finally, like I do think that in some sense, a lot of the issues I'm talking about seem really hard to deal with forever. That is, if you imagine trying to write down an algorithm that's going to keep working for the next 40 years or something, that seems really hard. And so in that case, what may end up happening, I think in some sense a reasonable guess, is that we build alignment techniques that work for a while, but over time, right, if we want to think about very far future AI systems, actually between now and then, much of the new research that is done might be done by machines. So it might end up in the world where like we have done some amount of AI alignment. We've hopefully built systems which are trying to help us like navigate challenges we face in the world. One of those challenges is aligning AI systems. So eventually you end up in this world where a lot of our work is itself being done by machines. And that's another way in which I do think that like powerful AI systems will ultimately be sort of working alongside us in this kind of work I'm talking about in this talk. And that's exactly how that goes. Is like it's really hard to say what's going to happen. That it will be exciting.
Yeah, it sounds like a very different world.
Yeah, I often think about very science fiction-y worlds, and it'll be interesting to see how this all plays out.
Yeah. And we have one last question. Do you have any closing remarks or advice for our audience who are mostly maybe graduate students in AI?
I should have prepared something. This is a very natural question to receive. I mean, I think at a high level, sort of, there are, I think, many interesting questions in AI alignment. I think different questions will probably appeal to different people. This talk, I think, really pointed at like one question I think was probably fairly deep in the weeds. But I think there's sort of a surprisingly, like the ratio of problems to people is like truly quite extreme. I think this problem is fairly likely to become important very, very quickly. So I think just anyone who is interested, I definitely recommend like getting into the details in some of these questions. And like, I think it's pretty rewarding to spend time engaging with them, either in the context of sort of more conceptual work, like what I was talking about in this talk, or in the context of like engaging with large language models or engaging with, interpreting existing deep learning systems. I think all of these are just like, there is a lot to do here. And I think that like, it's going to be interesting over the coming years as I suspect there's like going to continue to be pretty good growth in people and interest. So hopefully it's like a reasonable forward-looking thing to do from a career perspective, but I can make no promises there.